Hello everyone. In this video we're going to provide an overview for chapter 3 of On's book Discrete Distributions. So my name is Fred Rispoli. So the overview is broken down like this. These roughly are aligned with the different sections in the textbook. You can see we have a list, a lot of topics, but some of them are very short. So we'll begin with random variables. Random variable is an important idea in probability. The idea is a random variable, which I'll abbreviate as RV, is any function that assigns a numerical value to each possible outcome of an experiment. So it's sort of like we're taking the sample space, and to each outcome in the sample space, we make sure there is a number assigned to it. Now there are two types of random variables. There's discrete and there's continuous. Discrete random variables have a countable number of possible values. Just like a discrete set, they can be placed into a one-to-one correspondence with the integers or they're finite. And continuous random variables can take on any value in an interval. They cannot be enumerated. These types of variables are closely aligned with the real numbers. So one example is, let's let x be the number of heads obtained in 3 tosses of a fair coin. Then x is an example of a discrete random variable. We could let y be the amount of precipitation produced by a storm. Okay, so y is this type of measurement. Y is an example of a continuous random variable. Now, in the next section, we talk about probability distributions and the CDF. So we'll start out with this definition. Given a random variable x, a probability distribution is a function, f of x, that gives the probability that our random variable x is equal to a specific value of x. So you can see there's a bit of a convention here. Capital X is used to represent the random variable, and the lowercase values of x you should think of as specific cases of the random variable. So a couple of properties the function must satisfy. F of x must always be greater than or equal to 0. Right? And remember, f of x is giving the probability of x, so that always has to be greater than or equal to 0. And the sum of all the probabilities has to be 1. And of course, if you put these two together, this implies that f of x is really always between 0 and 1. So this type of function is called a probability mass function, right? For a discrete random variable, f is called the probability mass function, or sometimes abbreviated PMF. So here's an example. Suppose we're tossing a pair of die. So that is the experiment. We're tossing a pair of die, and we're looking at the sum of the two numbers on the die. So this gives us a discrete random variable x. X could be any number from 2 to 12. And if we think about the probabilities of x, right? So probability x is 2 is 1 over 36. X is 3 is 2 over 36. Okay. What we have down here is a discrete probability distribution, right? Very important one. One that you should know if you're interested in playing a lot of dice games. Okay, backgammon, for example. So you could see here, these are the different probabilities. If you were to add all of these up, you would see that they add up to 1. And notice that all of these values are greater than or equal to 0. So these two properties are satisfied. Now the CDF stands for the cumulative distribution function. Okay, and the cumulative gives you the sum of probabilities up to a certain x value. So we use lowercase f for the probability mass function, capital F for the cumulative distribution function, and over here we have less than or equal to for the CDF. Okay, so an example might be, suppose I have a random variable x. It could take on these 5 values, 0, 1, 2, 3, 4. These are the probabilities. Okay, so this would be my PMF, my probability mass function. Now the CDF is what we get when we look at, the cumulative value. So my first value for the CDF, capital F of 0, would be the same as this, 0.2401. Capital F of 1 is going to be the sum of these two values, the sum of the probabilities x equals 0 and x equals 1. So that's why we get 0.6517. Capital F of 2 would be the sum of these values, the probabilities for 0, 1, and 2. Okay, and so on. And you could see that this is going to max out at 1. So we could look at a graph of this, and you'd see that the graph might look a little bit like a step function. The key thing is you have these jumps at the whole numbers. So this is an example of a cumulative distribution function. In the next section, we look at the mean and the variance of discrete random variables. So the mean is also called expected value of a discrete random variable x. It's given by, here you see we have this notation, e of x, when we want to think of this as being closely associated to our random variable. It's also a mean, so you'll use this value mu sometimes to denote that it's a mean. And we calculate it by taking the sum of all the products. We look at x times f of x over all possible values of x. So this is a sum of products. So as an easy example, what's the expected number of heads in 3 tosses of a fair coin? Well, let's let capital X be our random variable. Right, it's our discrete random variable. Let it denote the number of heads in 3 tosses of a fair coin. Then you could see here we have our probability distribution. It's easy to figure out these probabilities from basic concepts that we talked about back in chapter 2. And then to get the expected value, we take x times f of x. So you can see here, these are the products. As we go along, the first column times the second column, we get these products. And then down here, we sum these up. So we have the sum of the products. So now that we have e of x, right, the expectation or the expected value of x, one variation of this is if we have some function of x, which does come up. Let's say we have a function h of x. We can talk about the expectation of h of x. Now here, we take the sum over all x of the product h of x times f of x. Right? Before we just had x, but now we have this function h of x times f of x. So one situation where this comes up a lot, we'll need to calculate e of x squared. So what we would do is you square the x values first, then you multiply by the probabilities, and then you sum all of them up. So that's what this tells us here. Square the x's, multiply by the corresponding probability, and then add all of those up. So we'll need this in the shortcut formula I'm going to show you in a few seconds. So if we think of e of x as the mean, we could also talk about the variance of x. Okay, so here we might use this notation, VAR of x, or we could think of this as sigma squared. So we could define this variance as the sum of x minus mu squared times our probabilities f of x. So that's similar to the definition of variance of just a set of numbers. But a formula that will prove in the class notes and in the textbook is what I call the shortcut formula. And this tells us that the variance of x is equal to e of x squared minus the mean squared. So if you have a data set, you have maybe three or four values in the probabilities. It's about the same amount of work whether you do it this way or this way. But once you go beyond that, 4, 5, 6, 10 different values, the shortcut formula really is much faster. The binomial distribution. All right, the binomial distribution is used in a lot of applications. We could think of x as a binomial random variable, sometimes abbreviated bin NP, if n is a fixed number of Bernoulli trials. So these are trials that can result in either success or failure outcomes. P is the probability of success in each trial, which remains constant from one trial to another. Now x is the number of successes in n trials. So a really important distribution. Even in financial applications it comes up, medical applications, many different applications. And here are some examples. So these are examples where x follows a binomial distribution. If one is providing medical treatments to n subjects, you record whether each subject, survived, okay, or is cured. X would be the number of survivors among the n subjects. If I took a survey, and I often do this in the classroom, I asked the question, if possible, would you go to outer space? Assume it didn't cost you anything and you had a chance to do it. Would you go to outer space? Let's say the trip was you leave somewhere, perhaps Florida, you go up, you break the Earth's atmosphere, you hang out in space for a while, and then you come back. It's interesting the results you see on this question, but for now, let's just think of why is this binomial? Well, let's let x be the number of people who answer yes. So you could see that if you had a group of, let's say, 50 people, x was the number of people who answered yes. S could take on any value from 0 to 50, right? If n is 50, you could see that x would be an example of a binomial random variable, and it follows a binomial distribution. We could also consider a group of n adults. Let x be the number who smoke cigarettes. So again, x would be a binomial random variable. Now, one of the advantages of talking about a random variable and describing it as a binomial is that once we know it's binomial, there are fast ways to find probabilities. So we would have formulas in the case of the binomial. If I wanted the probability that the random variable x is equal to x, we could use this formula, n choose x times p of x. Remember, p is the probability of a success on one trial, times 1 minus p to the power n minus x. So this would be the probability of failure. So when we need to calculate probabilities from a binomial distribution, we'll look at 3 ways to find the probabilities. The first way is using this formula. Okay, and this calculates what I would call exact probabilities. Probability x is equal to 5, for example. Another way to find probabilities is to use the table. So it's extremely important to know how to use the binomial table that's in the appendix of the book. So you'll see examples of this in the notes. And then finally, we could find these probabilities using either R or some other software. Excel does a pretty good job with these. Lots of other software that'll do it. Or some technology, calculators that do statistics, also pretty easy to use to find binomial probabilities. One last item I'll mention here about binomial random variables is it's very easy to calculate the mean and the variance. You don't have to use some of those formulas that we just talked about when your random variable is binomial. If it's binomial, the mean is just n times p. Very quickly you get a mean, and the variance, not much harder, n times p times 1 minus p. So that's much faster to get it like this compared to the other formulas that I was showing you before. But remember, this is only true for a binomial random variable. But still, this will come up often later on in the course. Next, let's take a look at a hypergeometric distribution. The hypergeometric is a distribution, it's discrete. It describes the probability of x successes in n draws without replacement. Right? One thing to make a note of here, the binomial is like sampling with replacement. Here we're sampling without replacement from a finite population of size capital N. And this population contains exactly, let's say, A objects that we'll call a success, wherein each draw is either a success or failure. So the probability that our random variable x is equal to a certain value, okay, is equal to a choose x times n minus a choose n minus x over capital N, that's the size of your population, choose lowercase n, that's the size of the sample. So basically, we're choosing a sample of size n, and we want to know what's the probability that we get x successes when in the population there's a successful items, and then n minus a is the number of failure items. So the formula may seem a little complicated, but the reality is you can probably solve these problems without the formula. Just go back to some of the things you learned in chapter 2, and you could come up with correct answers. Okay, another distribution here is the Poisson distribution. So here we have the following conditions. the probability an event occurs in the interval is proportional to the length of the interval. All right, so that's one condition. The second, two events cannot occur at exactly the same instant. And the third is that events occur independently. So some examples here might be the number of hurricanes that Florida gets in a winter. Okay, or the number of arrivals that occur at a stoplight over a period of, let's say, 10 minutes. So we say the probability is proportional. So if we knew the average amount in 10 minutes, then we could easily figure out the average amount in 20 minutes. So that's the sort of thing that we're talking about. So we could find the probability of X events occurring over a time period for a Poisson random variable with parameter lambda using this formula. Okay, so the probability of X occurrences is lambda to the X e to the minus lambda over X factorial, where e is this famous number. It's the base of the natural log. You can see it's approximately 2.7. And once again, there are some simple formulas for the mean and the variance. The mean for a Poisson is simply lambda, and the variance also is just lambda. So if you know your random variable follows a Poisson distribution, and you know the average number of occurrences, then you could use this formula. So here are a couple examples. In general, we could take the number of occurrences in a given time or area. I mentioned Florida, the number of hurricanes in Florida during a certain year. Number of arrivals at a toll booth, really this should be over a certain period of time. And an interesting one, the number of hits a website gets in 1 minute. All of these follow a Poisson distribution. And once again, we get 3 ways to calculate these. Okay, just like with the binomial, you could use the formula I just showed you. There's a table, and we could use R or some other technology. So you should have practice with all 3 of these. As you go through the notes and the book, you'll see examples. Here's one example based on website hits. Suppose the number of hits on a certain website follows a Poisson with a mean rate of 4 per minute. What's the probability that 5 hits are received in a minute? It's the probability that you get at least 70 hits received in 15 minutes. So we can set up our random variable X. X is the number of hits received in t minutes. Then we know X is Poisson, and the average here would be 4t, right? It's an average of 4 per minute. We have t minutes. Lambda is 4t. So for 1 minute, we could figure out the probability that X is 5, e to the minus 4 times 4 to the 5th over 5 factorial. Simplify this, get 0.1563. If I wanted to calculate the probability of at least 70 hits in 15 minutes, okay, well, 15 minutes, I need to think of what my lambda is. We know lambda is always 4 times t, so 4 times 15 is 60. We want the probability X is greater than or equal to 70. So we'll use the rule of the complement. 1 minus P of 1 minus the probability X is less than or equal to 69. So this could be hard if you did it using the formula, right? It's ridiculous if you did it using the formula. You can't use a table. So here's an example of a problem where you have to use technology. So we would solve something like this using R. It would be 1 minus the cumulative version of the Poisson formula, 69, 60. We would get 0.112. Okay, next we have the geometric distribution. So this applies when you have a situation where each trial can be either success or failure. The trials are independent. The probability of a success stays constant at P. And the idea is you continue until the first success is observed. So for example, if you were coin flipping, you would want to know, let's say, what's the probability you get your first head on the fifth flip? Okay, so that would be appropriate here. We'd use this geometric distribution. Here we have the probability is P, the probability of success, times 1 minus P, the probability of failure, to the power x minus 1. So again, you could probably figure out answers to this type of probability question without the formula. But I put it here so that you see most of the often discussed distributions. And here we get a simple formula for E of x. It's just 1 over P. Thank you very much. Okay, and finally, we have Chebyshev's theorem, which I'll mention is covered on a separate video. So please watch that video. This comes up near the end of the chapter. And there was not a lot discussed about Chebyshev's theorem, but it's an important theorem. So you'll see that covered on a separate video. And the last item we have here is the multinomial distribution. So this is a generalization of the binomial. The difference here is that you have trials that can result, let's say, in k different outcomes. Okay, the binomial could result in 2 outcomes. You might have a situation where you have 3 outcomes or more. So if we let P of I be the probability of outcome I on any trial, and our random variable xi is the number of trials resulting in outcome I, then we get this PMF, this probability function, n factorial over x1 factorial times x2 factorial and so on up to xk factorial. And these are the probabilities raised to the corresponding powers. Okay, so that's most of the material. I'm just going to finish this video with an interesting game where some of these probabilities can be applied. There's a famous game called Chuck-a-Luck, where a player bets on one of the numbers 1 through 6. These are based on numbers off a die. Then 3 dice are rolled. If the number appears 1 time, then the amount won is, let's say, $1. Now here, I've written this out where it says if the number appears I times, the amount won is $I. So if the number that the player chooses appears once, then $1 is won. If the number that the person chooses is $2 is won. If the number is $3 is won. If the number does not appear at all, then the player loses $1. And here we're interested in our random variable x is the amount won or lost, and the expectation of x. So here's an example of the probability distribution for this. Okay, we could work all of these numbers out. We get the probability distribution. So It's an interesting game where we could use many of the ideas that we see in this chapter. But I mention it because it's an interesting project for students to write a computer simulation of this. I know I had students in the past that were interested in it. And you could see this, this game analyzed and even some of the key ideas to writing the simulation in this paper of mine called Constructing a Spreadsheet Simulation Model of Chuck-a-Luck, an Application of Logic Functions. Okay, so this concludes the video. Hopefully you now have a good overview of Chapter 3, and you could go on and go through the material in the book and the class notes.